So, welcome. Today we're going to start talking about simultaneous equations. Now, just to start off with, just a bit of a recap of some of the things we've learned about linear relationships so far. You'll remember that we have our general form here, which is our y equals mx plus c, where m is the gradient, or sometimes we call this the slope of the line. So we think about the steepness of the line. And c indicates the y-intercept of the graph. Couple of other little things that you should remember, you absolutely should remember, that to find the x-intercept, make y equal to 0 and solve for x. And to find the y-intercept, make x equal to 0 and solve for y. So you absolutely have to remember the x-intercept occurs when y is equal to 0 and the y-intercept occurs when x is equal to 0. Those are facts you absolutely have to remember. Okay, simultaneous equations. So these occur when two or more lines intersect or cross on the axes or on the Cartesian plane. So there is a point that belongs to more than one line. So our lines, they consist of multiple points. Okay, that's what a line is. It's just lots and lots of points. So whenever we are looking at a line, we're just seeing if a point is on that line. And we're seeing if they share a point, if there's a point that's on more than one, or in other words, where they intersect. And that's a solution. Okay, that's a solution, and of course have a coordinate x, y. And you can solve that system of equations, and that's what we call it when we have two or more equations. We can do it graphically, which is on the graph, or visually, or algebraically. We're going to start off doing it graphically on the graph. Drawing. So this means you are going to have to draw your graphs very, very accurately. Okay, so I hope you all have rulers. You should have. So let's talk about a few situations to begin with. So equations with no solutions. This happens when there's no intersection, and therefore no points in common. This happens when the lines are parallel with each other. So remember, parallel lines are when lines run next to each other, but never actually get any closer or further apart, so they never are going to cross. So that's why there's no solution, because they don't intersect. So here I've got two equations on the graph that are parallel with no intersection. How do I know that they are parallel? They have the same gradient. The gradient on both of them is -2. So when lines have the same gradient, the same slope, that means that they are parallel and they are not going to cross. Another situation is when they have multiple solutions. So, in other words, there's no unique solution. So when our lines cross nicely like that there is what we like to call the solution. Okay, that's where they cross. And that's one point. It's a unique solution. But here, there is no unique solution, because the lines are actually on top of each other. So there's no one point at which they intersect. They actually intersect every single point because they lie on top of each other. And I'll just erase all that. Now, if you can see here, I've got my equations here, a red one and a blue one. Might be a bit tricky to see, so I'll just see if I can zoom up a little bit. There we go. You can see that they actually lie on top of each other. And can you see why they lie on top of each other? if you said that they are the same equation, you'd be correct. 10 points for Gryffindor. So this example shows two equations that lie on top of each other. So they are equal to each other. Every point is a potential solution, so there is no unique solution. That's why we say there are multiple solutions. It's not very handy for us when we're trying to find an intersection, but that can go more into what we do later in algebra, in methods and things. Now you might remember perpendicular lines. This is when lines meet at right angles, 90 degrees. So these lines have negative reciprocal gradients. So to know if these lines are perpendicular, you use the rule. Gradient of one equation is equal to -1 over the gradient of the other. The other way of writing that is that the two gradients times together give you -1. And you probably remember that from earlier in the year or through your other study. Here I've got a little example of where two lines, they intersect right there, and they are perpendicular to each other. And you can see that they are negative reciprocals of each other. Okay. Let's start looking at solving some of these graphically. Okay, so use the graphs to find the solution of the simultaneous equations. Solution of the simultaneous equations. So we've been given the equations, but if we weren't, we would have to read this from the graph. So this first one, I can see it intersects there, which is of course at 2, 1. Okay, and here they intersect, which is at 1.0 and 1. So you can see you've got to be reading these graphs very carefully. So if you've drawn them, you have to be very accurate in order to get an accurate intersection. Now obviously there is ways to solve these algebraically, which we'll get to later in the week. So for the following simultaneous equations, use substitution to check if the given pair of coordinates is a solution. So remember, substitution is where we sub in that value into an equation, and we want to see whether it's true or false. So let's do it for this first one. So A. So I've got 3x plus 2y equals 31. 2x plus 3y equals 28. And we're subbing in 7 and 5. Okay, so let's sub in I'll call that equation 1 and equation 2. So let's sub into equation 1 first. So I'll sub in, subbing that coordinate. So that means 3 times 7 plus 2 times 5 equals 31. So 21 plus 10 equals 31. I'm going a bit over the page. 31 equals 31. Okay, so far so good. Let's do it for equation 2. You have to do it for both to see if the point lies on both lines. So 7, 5. So subbing 2 times 7 plus 3 times 5 equals 31. So that's 14 plus 15. That's 29. That does not equal 31. So therefore, 7.5 is not a solution. Okay. B, we've got y minus x equals 4. Yep. And 2y plus x equals 17. I'll call that equation 1. Equation 2, and we're going to sub in 3, 7 first into equation 1. Well, 7 minus 3 equals 4. Yes, so far so good. So equation 2, again subbing in 3, 7. Got 2 times 7 plus 3 equals 17. So 14 plus 3. Yes, indeed, it does equals 17. So therefore, 3, 7 is a solution. Okay. Next one. Solve each of the following pairs of simultaneous equations using a graphical method. Okay, it does specify using a graphical method. So that means you have to draw the graph and you have to draw it accurately. Now, you can have a ruler and of course lines. I don't have that on here, but I'm going to do the best I can. I'll just try question 3. Okay. And do, oops. Let's try that again. Now, these equations are in the form of are in the intercept form, so that makes life a bit easier for us trying to sketch these graphs. Now remember, you must always label your axes, which is x, which is y, and use appropriate scale. Now, with a ruler you can do things a bit easier. Okay, so 3, 4, 5, 6, 7, 8. I'm trying to make them roughly equal. 2, 3, 4, 5, 6, 7, 8. I don't think I've done very well. So this one, equation 1, I might actually do different colour. So my x, 1, 2, 3, 4, and my y, and then you get your ruler. And you draw a nice straight line, obviously. Now, when I was doing this, I perhaps should be going 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, I can't just leave it like that. I have to label the intercept. So that intercept is at 5, 0. This intercept is at 0, 5. Okay, and my other one, doing red, my y-intercept is at 8, And my x-intercept is at 4. Okay, so looks like, oh, better writing. So that's at 4, 0. That's at 0, 8. And the intercept there. It'll be at 3, 2. If I'd drawn it a bit more accurately, that might be a bit clearer, but yes, I think that would be it. Yeah, and I just double checked that algebraically, and yes, that is my intercept. So yay, I managed to draw it accurately enough. But you have to use a ruler. Now, we haven't set this question, but I just want to run through a little bit about how to read it. So, at a well-known beach resort, it is possible to hire a jet ski by the hour in 2 different locations. On the northern beach, the cost is $20 plus $12 per hour. So cost is $20 plus $12 per hour. While on the southern beach, the cost is $8 plus $18 per hour. So the jet skis can be rented for up to 5 hours. So it first asks you to write the rules relating to the cost to the length of rental. Now if I was to write this, I would say equation 1 is the northern, and so cost equals $20 plus $12 per hour. Equation 2 is the southern, where cost equals $8 plus $18 per hour. Now when you set up your Cartesian plane, it's just going to be the first quadrant there, because obviously you can't go back in time and you can't have negative cost. You're not going to be paying your customers. So I'm going to be setting it up like that. So where H is our x-axis, length of rental, and the cost is our y-axis. But I would actually use C and H to indicate those ones. Now see if you can do that yourself, that question. Now that I've set it up for you, can you do it yourself?